All right, everybody, thank you for coming to the University of Idaho Integrated Design Lab Fall Lecture Series. Today is our last installments of the lecture series for this year, so thank you for sharing your evening with us. I'd like to thank our sponsors, NEA, the Northwest Energy Efficiency Alliance, and Idaho Power, for supporting and sponsoring education and training events like this, making them free for people to apply and to come to. Please remember to sign in and fill out your evaluations. We've got sign-up sheets over here on the table. We'll be sending those out later during the lecture as well. Please fill out your evaluations. The feedback and the sign-up sheets are pretty critical in getting these types of things funded through NEA and Idaho Power, so please take some time and fill those out for us. For those of you joining us online, you can send any of your questions to arch.dunn@gmail.com. That email address is located below the live link as well. And we'll pass on and relay any questions that you have to our speaker today. So with that, I would like to thank Heather Burpee for coming to present for us today. She's a fellow IBLer. She hails from the lab in the Pacific Northwest in Seattle. And currently there, she is a research assistant professor and health design specialist at the University of Washington Integrated Design Lab. She consults leading health design firms in the Puget Sound region on best practices for high-quality, energy-efficient design for hospitals. She has recently organized some educational field trips to Scandinavia to check out some high-performance hospitals there, and she'll be talking about her research on a project called Targeting 100. So with that, would you please help me in welcoming Heather Burpee to our lab?
Thank you all for coming today, and thank you for inviting me to speak here. And we have a relatively small group, so what I'll say is if you have questions as I go, please feel free to ask them and make it a little bit more conversational along the way. And for those of you online, send in your email questions. As Jake mentioned, I'm from the University of Washington, which is in Seattle, and I'm part of the College of Built Environments there in the Department of Architecture. We have a small group that's called the Integrated Design Lab, much like this Integrated Design Lab here in Boise. And the work that I'm going to be talking about today is funded by the Northwest Energy Efficiency Alliance and the U.S. Department of Energy through the Recovery Act. So my job for the last 2.5 years has been a Green Recovery Act job, so I'm thankful to that program. I'm just going to grab my pointer here. So we're going to be talking about healthcare energy efficiency today, and I'm just going to set up the problem a little bit. I know that some of you are familiar faces, so you've seen some of this information before, but I think it's worth going over again. Healthcare represents a huge portion of the amount of energy expended in the United States. 5% of all energy in the U.S. is used by healthcare. I say that's a huge percentage. That includes all buildings, all transportation, and if we look on a global scale, that translates to 1% of all global energy is devoted to U.S. healthcare. So this is a big target of opportunity for energy reduction and carbon reduction and the ultimate health consequences that energy use represents. So I'm going to be talking a lot about energy today and focusing mostly on that, but our work also looks at what we like to characterize as high-performance healthcare. So that's also the quality of the built environment. How does the hospital fit into the city, and how does it become a community resource? How can the occupants of the building, patients, staff, have access to daylight, fresh air, views, and green space? So these are also important things in our work, and I'll touch back on a few of them. I won't emphasize them in this presentation, but they are a big part of our work as well. Daylight specifically is at the core of our lab. We started as a daylighting lab, and we think it's a really important attribute of a high-performance building. And I'm just putting this reference up here so that you might go back and look at it later. I think it's a really great article published in Scientific American in May of 2011. And it talks about the change in science around daylight and our understanding of how daylight affects our biological systems, and specifically circadian rhythm. And what the basics of this science is that the light that we have that goes through our eyes isn't just for seeing, it's also striking hormonal balances in our body. And so light is something that we need physiologically to be healthy. We need bright light during the day and true dark during the night for these cycles to function properly. And this is really new science that emerged in the early 2000s, and that there's an innervation pathway, so the nerves are a separate pathway for the biological aspects, different than seeing. And so as architects, this is a really important piece of information to know as we develop buildings and how we bring in daylight to those buildings. Specifically in healthcare, healthcare buildings can be really deep span structures where there are a lot of spaces that don't have access to daylight. And for staff that work 12-hour shifts, often going to work in the dark, going home in the dark, this is a really important thing to keep in mind as we put together these new facilities. So I'm going to transition, though, into the Targeting 100 work, and I'll mention back some of that daylighting and how it played a role in this project. Targeting 100 developed from a Pacific Northwest model into a national model for looking at really 3 goals. One is, how do we meet the 2030 challenge in a hospital? How much does it cost to construct a hospital that meets the 2030 challenge? And we really want to disseminate this information. We want to make it so that people that are charged with building new hospitals can use it, implement it today. A little bit about the 2030 challenge. I don't have a slide on that, but essentially it's an energy goal, and it's a progressively intense energy goal. So today, the 2030 challenge for today is a 60% reduction from operational hospital energy use. And it progresses to 70, 80% to eventually carbon neutral in 2030. So for this project, we're looking at the 60% reduction goal. I'll talk a little bit later about that. And we're looking at 6 cities across the US. So really they're the 6 most populous cities in the most diverse climate regions across the US. And you can see them here on this map. There's Seattle, Chicago, New York, Los Angeles, Phoenix, and Houston. And we've been working on this project for the last 2.5 years at the national scale, for the last 7 years in the Pacific Northwest, in really close collaboration with Solarc Architecture and Engineering, Mike Hatton specifically, TBD Consulting, which is a cost consulting group, and Martin Connor in that group, and NBBJ, primarily with Duncan Griffin and Dwayne Johnlin. So kind of to go back a little bit and talk about what is an energy baseline for a hospital. I mentioned at the beginning they're really big energy consumers, so this starts putting that in context. So in the Pacific Northwest, typical operational acute care hospitals use about 225 to 350 kBtu per square foot year. We see examples that are up to 450, so there are definitely outliers. And to compare that to an office building in Seattle, offices use about 70 kBtu per square foot year. Does everybody know what an EUI is and these numbers that I'm talking about? Okay, so we're looking at being able to compare in a comparable way buildings to each other. So these represent big energy users. And so this baseline is the fundamental starting point. For the 2030 challenge, the baseline that is recommended is the baseline that you get out of Target Finder. And how many people have used Target Finder? Do you guys know Target Finder? So I'll talk a little bit about it. It's a tool that has been developed by the EPA, and we know about Energy Star equipment like dishwashers and refrigerators and things, but buildings can also have an Energy Star rating. And Target Finder is where you start to become an Energy Star building. And so what you do is you enter the type of building that you're looking at, the size, and some other parameters. In this case, for hospitals, the number of staff and the number of MRI machines. And it gives you an answer. That talks about what the median building of that type is, how much energy that type of building uses. For hospitals, so for most buildings, it accesses a data set called CBEX, which is the Commercial Building Energy Consumption Survey. For hospitals, it's a different database. They just redid the database in 2010. And the reason I'm kind of getting into this nitty-gritty detail is the database changed the fundamental baseline that we're looking at for meeting the 2030 challenge. This graph is showing the 2010 Target Finder baseline, which is in blue, and in gray is the new 2012 Target Finder baseline for each of our 6 study cities, using the same parameters, the same size, number of beds, MRI machines, et cetera. And we can see how some of the numbers between 2010 and 12 shifted. New York stayed about the same, Los Angeles dropped, Phoenix went up, and it's kind of all over the board. They're all high, but New York is, in our estimation, artificially low. we don't, and the quality of the database, we're wondering about. We just really don't know. So for this project, since the baseline is such a fundamental part of it, we've decided, rather than relying on this 60% reduction from baseline in each city, we're just going to target 100. So an EUI of 100 kBTU per square foot year, which represents a 60% reduction from the typical national energy use for a hospital at 250 kBTU per square foot year. So ultimately our goal is targeting 100. And that's where the name of the project comes from. We've been working with a lot of different firms across the US in this work. In each of our study cities, we've had 2 separate peer review meetings where we've put this work in front of key stakeholders in the design, construction, operation of hospitals to get their feedback. And those meetings really influenced the trajectory of this work, where their feedback really changed some of the fundamental pieces of the research. And really our goal in that was to make sure that the work is grounded in the realities of design and construction of hospitals, and that this work could be implemented tomorrow if there was motivation by the hospital ownership and design team to meet this kind of aggressive energy target. So these are just some of the names of the organizations that we've met with across the US. One of the parts of this project was that we really wanted to understand how an operational hospital used energy in reality. We started this work 7 years ago, as I mentioned, and there was just no data on how hospitals use energy. And we searched really internationally for information about how hospitals use energy. And we could find maybe the overall EUI, like we've been talking about, but not how those component end uses filled in that EUI. So we worked with Legacy Salmon Creek Medical Center, which is located in Vancouver, Washington, to really develop a better understanding of how the energy profile of a hospital works. And I talked about our peer review process, and this was actually an outcome of our original peer review in the Pacific Northwest, where one of our collaborators, who is a hospital operator, he's a facility manager at a hospital in Olympia, Washington, said, your number for domestic hot water in your energy model is way too high. But we didn't have a basis to know where it should be because that data just wasn't available. So that's why we went here. We used it was a really fortunate example to be able to look at, in that they had a great digital control system with a lot of points already set up that they'd been monitoring over several years. So we were able to use that data, then supplement it with our own monitoring. So for example, we looked at the reheat loop and understood how much heat was being lost through the building, so we could really know how much energy was being used for that end use. Some of the things that, I want to see what my next slide is here. Okay, so I'm going to talk about it on this slide. Some of the things that we learned from this study, just high level, is that we knew that reheat was a big load in hospitals, and we knew that that was probably the big target of opportunity for energy savings in hospitals. This confirmed it. It's over 40% of the overall energy use of the hospital. So we knew that was one of the first places that we were going to look for energy savings. Some of the kind of other confirmations were this service hot water, 2%. And that goes back to that peer reviewer's comment that domestic hot water is just not as high as we'd originally modeled. We'd originally modeled this at 15%. So what that really translates to is patients aren't taking showers at hospitals anymore. When they're that well, they go home. And so we're not using as much hot water as we used to. Another surprise, actually, and modification to our model was this imaging number. That represents all the MRIs and X-rays and those big, heavy imaging equipment. And it's a really small part of the overall energy use. And when we started this project, we just didn't know, what's the way to solve the energy problem in hospitals? Maybe it's to take all the MRIs out and put them out in the parking lot and make them more efficient somehow. But this data shows that's really not the way to make a hospital more energy efficient. It's not using much of the energy. So we were able to use that in developing what our energy goals were and the strategies to accomplish those goals. And this data has been utilized across the US. It's really been a data set that people have been wanting to have and have been using. And essentially, we used the data to feed into our energy models to make sure our energy models were more predictive of actual energy use. So as I mentioned, the goals of Targeting 100 meet the 2030 challenge, which is represented by this graph. Average US hospitals are about 250 kBtu square foot down to 100 in these 6 cities. And understand the first capital cost investment. So, yeah, please.
Going back 2 slides, a big slice there is miscellaneous equipment. I just wondered, what does that include if it's not?
So that's a great question, and at the end I'll circle back to that. That's a huge chunk, and it's the computers, the IV pumps, anything that plugs into the wall. And right now, and I'll say this again at the end, that's the next target of opportunity, in that we don't really know, if we wanted to take the same approach and disaggregate this piece, we don't really know what those pieces are in a hospital. So that's really, in my mind, one of the next frontiers. So to test these ideas, we developed a scientific method to look at them, and we developed 2 architectural schemes. And I'll speak about those a little bit. The scheme A on the left is meant to be the typical US hospital today, deep diagnostic and treatment with a patient tower. This is a simplification of that, artificially simple. On the right is a model that's based in our work in Scandinavia and looking at how do we develop a model that brings more daylight, potential for views, potential for natural ventilation into the architecture. And so it has planned enclosed courtyards that drive down into the diagnostic and treatment and into the patient towers, which you can see here. And so while we didn't realize we didn't use natural ventilation in the patient rooms, it has the opportunity for that and has the opportunity to be a more resilient type of architecture. So between the 2, we kept as much constant as we could. They're both 225 beds, 477,000 square feet. They have the same window to wall ratio, though Scheme B has twice as many windows as Scheme A because it has twice as many walls. The ratio is the same. Approximate footprint. The massing models there are a little deceptive. They are about the same footprint, so they'd fit in the same kind of property. And then we looked at the same energy-related bundles. So we wanted to understand what's the energy difference between these 2 with one that's envelope-dominated versus internally dominated, and what's the first capital cost investment difference between the 2. And then we looked at 4 energy options for each. So each has a baseline. So we want to base this in, if you were to build a hospital today, not looking at any energy-related bundles, that's how much energy it would use. We used ASHRAE 90.1 2010, so it's really a future baseline. We wanted to be relevant and current. And then we looked at 3 high-performance models. I'm going to walk through each of these in a minute, but first I want to talk about, I'm going to separate out each of the architectural, building, mechanical, and plant systems just to clarify what we looked at. But that being said, we really think what's fundamental to this is the integrated strategies that go into it and the integration of teams. So it takes a lot of different experts sitting at the table from the beginning to make this happen, and it takes an integration of the technologies that are being implemented. And I'll talk a little bit about those technologies and the integration and how we approach that in this project. So and this is just one example of how we did this in this project. So fundamentally, we want to first reduce loads and then apply energy efficient technologies to those lower load regimes. So one way to do that is reduce solar gain on the envelope. So we're using exterior dynamic shading to reduce that solar heat gain. And what that does is it reduces, we want to both reduce the peak load and the load over the year. So this example is showing that, and I'll talk a little bit about this later when we look at the results, but here's the baseline peak load, and we want to reduce that peak load so that we can buy smaller equipment. So essentially, this represents how big the chiller is going to be. And if we can make the chiller this big, it costs a lot less. We also want to reduce the area under the curve. So the area under this curve, which is the baseline, is a lot bigger than the area under this curve. That represents how much energy you're buying over the year. So we want to reduce how much we're paying for energy over the year. So if we're able to reduce that peak load in the patient room, we're able to implement different building mechanical systems. So in this case, for Targeting 100, we chose to use a displacement ventilation system with radiant heating and radiant cooling. And that's just one way to do this, but essentially at the core, we want to decouple the heating and cooling from ventilation. And we're not able to do that unless we reduce that solar heat gain in the room. Displacement ventilation wouldn't work, and the radiant cooling panels would not be able to keep up with the higher peak load. And we'll talk a little bit about that later when we look at the data. Yeah.
Is that, I can't remember, was the radiant systems for the what you saw mostly in Europe, right?
Right, so really ubiquitously, radiant heating panels are used for heating, and the cooling is actually taken care of in the air and at a really low air change rate. So same as what we would be required to do by code here, but they don't ramp it up. So what we're required to do here is 4 air changes per hour when we do this kind of system. And in Europe, what you see is 4 air changes per hour with all the cooling that's needed in those 4 air changes, and then radiant heating at the window. We chose to put radiant cooling in as well. Some of the climates, like Phoenix and Houston, are a lot more extreme than some of the Scandinavian countries. So you need that cooling. You need a little bit more spot cooling here. And our temperature, the temperature range that's acceptable here is narrower. So we need to be able to have that cooling. So implementing systems, these decoupled systems, radiant heating, delivering the heat and cool via water versus air, gives you the ability to either have more flexibility in the floor-to-floor height, so more flexibility in that mechanical space, or it allows you to reduce the floor-to-floor height. In Targeting 100, we took a 1-foot credit, so that we took it from 15 feet to 14 feet floor-to-floor, and that was conservative, really. We probably could have taken it down, but that translates to cost of construction, where we use that foot floor-to-floor height credit to pay for some of the other systems that were more expensive. And then the lower load profile over the year, it's more balanced between heating and cooling, and it's a lot smaller. So it enables efficient plant systems and smaller plant systems. So in this case, the ground-coupled heat pump plant, the bore field is much smaller than it would be under a non-reduced load regime. So essentially, this integration of systems is fundamental to this project. So I'm going to talk, having said that, I'm going to talk through each of the systems separately, just so we outline what the strategies are. So first, architectural systems, and I'm really going to talk about this briefly, but we decided to break the US up into the northern climates and the southern climates for this. So for the northern climates, for the baseline, we used ASHRAE's Zone 5 requirements. And for the southern zones, we used Zone 3. And so, for example, for Houston, the baseline is actually a little bit more high performance than they would have to implement. And then the high performance meets or exceeds that zone requirement. Now, that's not very specific, but what we did is we developed a performance-based standard, and this is really par for the course for the whole project, where we had a performance-based goal. And then we decided what products met that performance-based goal. Not to say that that's the only path to meet that performance standard, but we had to pick something because we needed to develop a cost model. So for the windows, we chose Solar Band 70 for the northern climate zones. For the southern, I think we chose Solar Band 60. And the way that we made the choice is we didn't want to choose a product that was artificially going to be really expensive, like a triple glazed, curtain wall that has never been implemented in the US to date. We wanted to pick something that's relatively standard, but high performance that works well. And the details of those numbers are going to be, I'll talk about the way that we're disseminating this information a little bit later, but they will be available, and I can send them as well. To be more specific about that. So that talks about the high performance envelope. I talked about solar control. We're talking about reducing direct solar heat gain in the spaces through using exterior dynamic shading. And the way that we approach this is putting the dynamic shading on the south, east, and west facades and not the north. So, and this is one strategy to reduce that solar heat gain and direct solar gain. And then daylighting, where we can, bringing in natural light and turning off the electric lights. So then building mechanical, this is where we realize a lot of the energy savings and where a lot of the energy waste is happening in hospitals today. So in the baseline system, it's really a VAV system. In the patient rooms, it's 6 air changes per hour, overhead mixing system. In the OR and ED and kitchen, it's a higher air change rate. It's the code minimum air change rate. And we chose VAV as the baseline. Some of the places across the country in our study cities, VAV really isn't the baseline. It's constant air volume is the baseline. So our baseline is actually a pretty high performance hospital as it is. In the high performance models, which, I'm gonna go back for a second. The high performance models, there are 3 of them, and they really only vary at the plant level, which we'll get to next. So all 3 high performance models use the same architectural systems, same building mechanical systems.
Are they using the CAV for the high latent load areas more?
I think it's more of an approach of constant is good. And so we're just and it's throughout. It's, I was speaking with somebody that was an engineer in Florida yesterday, and he was like, VAV is not our baseline. It's CAV everywhere. And it's, one of the things that we see here too is these are new systems, and there's perception of risk with something new, especially in a healthcare kind of climate. And VAV is new in some areas, right? For us, that's not new. And if we're going to do utility incentive programs, Seattle City Light and Puget Sound Energy probably don't consider constant air volume as a baseline. It's variable air volume. So we have to take into consideration the cultural climate of where we're working. And in Florida, the cultural climate is CAV as a baseline. So for the high performance models, as I talked about, we're decoupling the thermal tempering from the ventilation air. We're doing that through displacement ventilation with radiant cooling and heating. And I should say that this is mostly in the patient rooms, and really in 80% of the model, we're using that kind of system. In places like the OR, the ED, the kitchen, we're using a really high performance version of VAV still. It doesn't make sense to decouple in those areas. The requirement for air change rates is just too high. And so we used an overhead mixing systems in those more highly regulated spaces with the ability to massively turn down at night when they're not being used. So, and we'll see that in the data where the turn down is, and you can actually see the difference in energy use. So how many of you are familiar with displacement ventilation? So I'm going to talk a little bit about what that is and talk about the research that's gone into validating this as a good source of ventilation for hospitals. So essentially at the core of the concept is that the supply air is supplied low in the space, and it's using the natural piston effect of the air heating up and it moves up through the space, evacuating the air high in the space. And we worked really closely with Mazzetti and Stantec, who developed the initial work for this in healthcare and validated that it's a good method. And the way that they suggest doing that is putting the supply air grill at the base of the patient bed, so on the wall adjacent across from the patient foot, and putting the return or the exhaust above the patient head. And that's the way that the ventilation effectiveness is the highest in that case. And operationally, it makes the most sense. One of the things you want to be careful with that kind of system is that some wheelchair or bed or whatever doesn't get placed in front of that supply air grill and block it. So at the foot of the patient bed is the very highly trafficked area. It's not a place where medical equipment gets left as often. So it's a good place to put that supply air grill. And then putting the natural piston effect requires that the exhaust be high, and putting it above the patient room was shown to have the best ventilation effectiveness. This is the cover of the research that Mazzetti did with these collaborators to show that this is an effective way to supply air in healthcare patient rooms. And they developed this work in order to implement displacement ventilation in several hospitals in California. And since this report came out, the NIH has put their stamp of approval on this method as go ahead and do this. It's NIH approved. And there are at least two hospitals in California under construction now that are displacement ventilation hospitals. So it's a burgeoning way to do this, and showing to be effective. This is a CFD model that Mazzetti put together, and it represents a patient coughing. On the left is the overhead mixing system, and we can think of the air as this beaker of water just mixing around. It's relying on that mixing to evacuate the air. Excuse me. So that's on the left, an overhead mixing system at 6 air changes per hour. On the right is the displacement ventilation system, and you can see through this beaker that the supply air is supplied low, and the natural piston effect moves the air to the top, and it's exhausted high. What this is showing is this patient coughing, and it's unfortunate that it's red, but on the left, the air of the cough envelops the caretaker's head. On the right, it is evacuated before it envelops that person who's caring for the patient. And this, along with many other CFD models that they did, showed that displacement ventilation was actually more effective at evacuating the air than the overhead mixing system, even at fewer air changes per hour.
Does the system get affected at all in the cooling mode, which I noticed the radiant panels were on the roof, so they'll be cooling up the air up top and having it fall below and then coming up. So
right, that's a great question. You have a heating source on the wall, you have a cooling source on the ceiling, you have people, and they tested all that through this report, and they fundamentally understand it better than I did, but they showed that that's the method to do this most effectively, is to have the cooling on the ceiling, the heating on the wall, and the CFD models show that the air is moving in the right way. The second picture is another really important piece of this. On the left is displacement ventilation when there's solar heat gain in the room, so direct solar spot in the room. On the right is when there's some kind of shading device on the window. So this starts to highlight that in order to implement this kind of building mechanical system, we have to have that shading on the envelope. And the way that we like to talk about this is that the shading is actually part of the mechanical system. It's not a separate architectural element that can just be value engineered out. You have to have it in order for this mechanical system to work. So it's a fundamentally integrated system between architecture and mechanical. So finally, the plant systems. And I'll walk through all 4 of the plant systems. And as I mentioned, the high performance models only vary at this level. So first, the baseline plant, and fundamentally the box in the middle is meant to represent the hospital. And on the left, you have a boiler. On the right, you have a chiller. They don't talk to each other. They're often simultaneously running. Heating and cooling is happening at the same time in the hospital commonly. The first high-performance plant is actually modeled after the legacy Salmon Creek model, where we call it the distributed heat generation plant. So really fundamental at the core of this concept is the heat that is necessary for the hospital is produced at the grade that it's needed. So as an example, the boilers are serving the reheat loop. And then there are point of use steam generators, and there's domestic hot water. And all of those needs are heat at different temperatures, and so the equipment can work at its most energy efficient mode to develop the heat at the right grade. Again, in this example, there's a chiller and a cooling tower. So this is more of a heating side plant option. The second high performance plant, plant 3, fundamental at its core is the heat recovery chiller. So here the chiller and the boiler are working together to be a more efficient system. And we've added a supplemental boiler and a supplemental chiller here. And I mention that because probably most of the time the heat recovery chiller would be enough, but there are some peak moments during the year where more chiller is needed or more boiler is needed. And in the project, when we as a team were making decisions like this, you probably don't need them, but we always took the more conservative road because we didn't want to artificially deflate the cost model. We wanted to make sure we included elements like this that may, increase the cost a little bit, but it makes it a more robust system. Another example of that is that in Phoenix and Houston, we probably don't need the radiant heating panels at the window. They're warm climates. They don't need a lot of heat. There's probably 1 week in the whole year that both of those cities need them, but we kept them in for the cost model. And a design team, when they're actually implementing a Targeting 100 hospital, will do that analysis themselves and make that call. And we just made the call to put them in and be more conservative about it. So the fourth plant, the Plant 4, the third high performance plant, is the ground coupled heat pump plant. And so at the core, essentially the ground serves as a battery. It holds heat, or you can extract heat depending on what the hospital needs. There are central plant heat pumps, and the ground can be bypassed. If there's excess heat in one place of the hospital and there's need for heat in another place, it'll just go through the heat pump and be a circular system and bypass the ground. An important part of this is that we actually made a change after one of our peer review meetings where we had the bore field sized to the peak load, and essentially what that means is you have a lot more bores, and the bores are really expensive. And we made the decision, let's not size it on the peak, let's size it on the base load, and then have peaking, and what's not represented here, a peaking chiller and a peaking boiler, so that we could have smaller bore field, less expensive, but it still works in a really efficient way.
Just curious.
Yeah.
Dumping heat most of the time, like 90% of the time, is it charging the ground with heat, or is
It's
it
balanced.
It's balanced.
And that's really important for a ground source for the bore field. Because you don't want to, if it's really lopsided, the ground will either warm way up and you can't extract coolth anymore, or it'll cool way down and it'll freeze. There was a ice plant in South Seattle that it's still, the ground underneath it is frozen because they were so cool. So that was something that was important in sizing this, is making sure you had that balance. And that's a good transition. So we're starting to get into the data here. So what this plot is the annual loads graph. Excuse me. So on the x-axis, we see the year, so January through December. And on the y-axis, we see the coil loads. In red is the heating, and in blue is the cool. And so to be more energy efficient, you'd want to approach 0 for both the heating and the cooling. This is the baseline, and we're looking at New York here. I just chose New York. It's probably not too similar to Boise, but more similar to Boise than Seattle. So the peak here, what I talked about earlier was we want to both reduce the peak load here and the area under the curve for both the heating. So here's the heating peak and the area under this curve. And we can see each of the cities across the US, and they're actually remarkably pretty similar. They're very different climates, but remarkably similar loads graphs. You can see Houston has more of a shoulder on the cooling than Seattle, for example, is a more mild climate on the cooling side. This graphic is a little preview to our tool. So the dissemination method for this data, we, in our original Pacific Northwest Targeting 100 model, we developed a full report, which was like 250 pages long with all the energy model data and all the cost model data and all the assumptions that went into both. And we made a decision as a team, we didn't want to multiply that by 6 and have 6 250-page reports that you all probably will never look at, and they'll collect dust on your shelf. So what we decided pretty early on is that we wanted to do some kind of digital dissemination model. And what we've been developing is a website, so you can access this information and look at what you're interested in and just bypass what you're not. And here you can see that for the loads, for example, you can click through each of the cities and you can get the big graph of the loads data. Here's the high performance model. In a second, I'll show them overlaid. You can see that the peak is reduced, the area under the curve is reduced. And this heating piece, it almost looks like a mistake here. It looks like we've accidentally plotted it twice. But what that is it's the turn down of the OR and ED at night. And you can see that difference that it makes in the heating load. So it's pretty interesting to see, in a graph like that, the results of some of the efforts you put in. And why that is each of these dots is representing an hour. So it's just the plotting. It looks like it's overlapped, but it's actually offset a little bit. So here they are overlaid, and you can see the change, the relative change of the peak and the area under the curve for both cooling and heating. We also looked at some of the zone loads. So this is coming back to that solar gain issue, and this is representing the west facade. So it's actually highlighted incorrectly on the plan, so it's over here on the plan. And we're looking at a block of patient rooms. And again, across the x-axis is the year, and the y-axis is the load. And the orange is the baseline, and the blue is high performance. So you can see the effect of the shading here. It's pretty remarkable. This is the New York data. You can see the other data on the left. It's less pronounced in Houston, lower latitude. Here's the peak day. So going back to this graph, this one day is the peak day. So we've graphed that day. And what you can see is this huge peak in the afternoon, which makes sense, right? The afternoon sun's coming around the west, and it's making the room really hot. And then the solar shading has the effect of just lopping off that peak. And why that's important is the radiant cooling panels can only keep up with so much load. They can't keep up with this load. So it's important to lop that off, not to mention the displacement ventilation issue.
Dynamic shades.
Yeah, so this is exterior dynamic shades. And I'm just going to go back to this plan if you can see it. This is the scheme A, so that baseline scheme. And we put them on the west, south, and east facades only.
And this is just the solar load, just from the sun. Do you know how it compares to the other loads? Is it the most significant in terms of the cooling, or?
That's a good question. Yeah, as far as the cooling, definitely. Yep,
Yeah,
definitely. I mean, we don't have people, lights, equipment on this graph, but this trumps all of that for sure. But that's why it's important to also lop this off, because there are other loads. This blue line is just the solar load, so it's actually higher. And those radiant cooling panels are not going to be able to accommodate much more than 6 BTU per hour per square foot. So here's the annual energy use, the EUIs, the results. So I'm going to walk through this a little bit. This is the slide that a lot of people are wanting to get to right at the beginning. Did you meet the 2030 challenge? So the answer is yes, mostly. So the gray bars are that target finder number. So even though I said we're ignoring that for this project, I've put it on this graph so that we can see the difference. The next one is the baseline. So this is if you built to code the ASHRAE 2010 and plants 2, 3, and 4, which are the distributed heating plant, heat recovery chiller plant, and the ground coupled heat pump plant for each city. And what we see is the percent reduction that's noted on each of these is percent reduction from this target finder baseline, which for the 2030 challenge would need to equal 60% to get there. Most cities we make it, but here's another look at New York. Our baseline is higher than what they report operational baseline. So it brings into question that operational baseline. Are hospitals being built today really less efficient than what's actually operating in New York today? Probably not. There are some hypotheses why this would be low, potentially because of district systems. There's a lot of district heating in New York. The New York peer reviewer said, well, it's because we're more compact. There's more going on per square foot, so we're more efficient. Not sure that argument goes that direction, but in any case, it doesn't really matter. The 100 is our goal. So we can see in this graph, and I should mention that we're at about a 90% draft. So if you see these numbers at the beginning of the year in our tool, they might be a little different, but conceptually, the answers are going to be the same. It's very similar. And I think our energy models are actually a little lower than these numbers now. There were a few tweaks that we made. But Gunnar has a comment.
What change did you make to the miscellaneous limits?
There's just a little bit of credit for Energy Star computers, and you know, it's more of a fundamental blanket kind of strategy that's not,
They're almost 50% of the loads after you get down to.
right. So that'll be like a couple of slides from now, we'll talk about what are the new targets of opportunity. So one of the big things that we've reduced is that reheat load. And that was through that decoupling of heating and cooling from ventilation. The two cities that we don't meet the 2030 challenge in are, well, that we don't hit the targeting 100 goal in are Phoenix and Houston. And that makes sense. They're the cooling dominated climates, and so cooling is higher. Houston also has a lot of dehumidification, and we've developed a way to dehumidify that doesn't involve cooling all the air down, wringing the water out, and reheating everything back up. I was going to say something else about that, but I lost the train of thought. Oh, here's Gunner's transition. That's great. So looking between Scheme A and Scheme B, and again, this is New York data, but one of the things that we're noticing, and I'll go back to the last slide, is there's not a lot of regional variation, which is pretty interesting, right? We're looking at 6 cities because climates are so different, but the annual energy use profiles are actually remarkably the same. The solutions are remarkably the same to meet those energy goals, which is actually kind of exciting in that we know there's a path that we can take that's not super complicated. So the new targets of opportunity, we look at A versus B also. Not a big difference between A and B. We see that the loads are the energy use is a little higher for the envelope-dominated design in the baseline, but it also has a greater reduction. And that's partially because of the daylighting. It's partially because of the distribution system, but they're remarkably similar, really. That makes sense once we start to break down the problem. We know hospitals are an internally dominated load issue. So what I mean by that is the ventilation air is what drives the energy use. And we can only go so low on the ventilation rates. They're code regulated. So we can only go so low, and that's what's driving the energy use, especially in this, but in the top part of this graph, it's still the air change rates that are driving that. So once we start breaking that down and looking at what are the targets of opportunity, the fans, that's a big chunk now, lighting and misc loads, and it's almost, like Gunnar said, almost 50% of the problem now. So we're hoping in our next iteration of this work, we can look at target 50. So how can we start attacking these loads to reduce them even more? Savings. So across are all the cities on the bottom, and this is the cost to operate them on an annual basis. And you can see there's a big variation in utility rates across the US, which is no surprise. Some cities or areas are regulated, some are deregulated. So in some areas like Houston, it's really hard to put together an accurate rate structure in the energy model. Beyond that, there are some other interesting things here. You can see I'm just going to talk about Los Angeles for a minute, just to kind of break down this data. So you can see in the baseline model, this is how much natural gas they're using. The blue is how much electricity. We've massively reduced the amount of natural gas in each of the models, barely touched the electricity. So that's another, the next step to look at the electricity use. But there's something interesting happening here, and it has to do with the cost of electricity versus the cost of natural gas. And so you can see that the most energy efficient system, which is this ground coupled heat pump plant, is actually less energy cost savings than the more energy intensive high performance piece. So there's a 1% energy cost savings here, 30% here. And actually it's not Los Angeles. So if you're looking at LEED, this is really an interesting detail issue, that the more energy efficient option would get you less LEED points than the less energy efficient option. And it has to do with how much natural gas costs versus electricity and the peak electricity rate in Los Angeles. So it starts bubbling up some interesting conundrums that you might run into in a real project. So that was the energy and the energy cost. Now we're going to talk about first cost of construction. You're not meant to digest this chart, it's just for me to talk about. But ultimately, this is the summary sheet of a 200-page cost estimate that for just one city. And so there's a lot of data here, and that's the point. The energy models produce a lot of data. The cost models develop a lot of data. And the way that we went about this is we didn't use like a RS means calculator to look city to city. We actually went out to contractors in each city and cost line by line the energy efficiency measures. So in some cases, like Chicago, drywalling is very expensive, and so we represented that. In other cities, boilers are harder to acquire and they cost a certain amount. So it's a complicated question, and we really looked at this in as much detail as the energy model. As I mentioned, there are things that we did that gave us cost credits and other things that cost more. And the budget, the way that we looked at this is it really requires, like the integration of systems, an integrated budget. And budgets just tend to get so siloed, and architecture has one budget, mechanical has another budget, and it's a really rigid budget. And what we're proposing here requires an ability to shift between those membranes and shift budget between categories. This is just looking at the mechanical side. So kind of showing some of those cost adds and cost deducts. We'll look at a little more in detail. Blue is baseline. So in this example, the dry side distribution is more expensive for the baseline. That makes sense. There's the heating and cooling is being delivered through the air handling system. So the ductwork is more expensive. It's bigger in the baseline. In the high performance, where this is the baseline, the high performance models for wet side distribution are a lot more, and that makes sense. We're delivering the heat and cool through water in the high performance models, so the wet side distribution costs more. And so there's shifts happening, and that's the purpose of this, showing this. Overall, if we boil the cost models down to a national average, these are the results that we see. And again, this is like at a 75% draft, so these numbers might shift a little bit when you see the final results. So as I mentioned, we wanted to see what's the first cost of construction difference to look at this more perforated model. And we see it's about a 6% cost add, which makes sense. There's twice as many windows, there's twice as much walls, there's more interior partitions because of those things, because of the articulation. And Scheme A is a little artificially simple. So this number might be artificially high, actually. Then looking between the high performance models, and actually it's pretty similar between Scheme A and Scheme B, so I'm just gonna show one number. It ends up being about the same. To shift from a high performance model to plant 2 and 3, it's about a 3% cost add. For plant 4, which includes the bore field, it's about 5%. This number came from when we sized the bore field to the peak. So we're hoping this number is gonna go down a little bit. We're not sure yet. One of the things that we talk about with this doesn't include any utility incentives that might happen. It's our experience in the Puget Sound region that there are a lot of utility incentives to be had. A conservative estimate is that it would be about a 1% of the total capital cost of construction. So it would reduce these to 2 and 4% respectively. That's a conservative estimate.
I'm sorry,
Yeah.
Utility what?
So utility incentives. So the utilities will incent projects that are making more energy efficient decisions that are more expensive. So if we look at it as a whole building utility incentive, which happened, we worked a lot on the Swedish Issaquah project out in the Puget Sound region, and the utility incentive of that was the largest that Puget Sound Energy had ever given, and it was more than 1% of the project cost. So that's one way to look at it. Another thing to keep in mind with these numbers is that the design is really developed to a schematic level of detail. So this is really early cost modeling. So at that point in a project, there's often shifts going on in the budget anyway. 3% represents a lot of capital, but it's also a really small percentage to make up in other ways. Another thing that we do talk about with this is some hospital organizations, Providence is a really good example, hold a certain percentage of capital in their new construction projects for energy efficiency. So they hold 1.5% of the total project cost for energy efficiency. And if it meets a reasonable payback, which for them I believe is 5 to 10 years, then they use that pot of money to pay for the energy improvements. And so if that were the model, we got a utility incentive that was 1%, we have the 1.5% in reserve, this would be cost neutral for these two plant 2 and 3. So some of the key findings, integrated design, early energy goals, energy benchmarking, team collaboration, measurement of performance through the project are fundamental for meeting these kinds of energy goals. The approach that we took was first load reduction and then unique application of common efficient systems. These are systems that have been implemented in lots of commercial buildings, not necessarily in healthcare. There's growing examples of healthcare buildings applying these kinds of systems to their new construction projects. And if we do that, we can get the 60% energy savings, meet targeting 100 with little incremental capital costs, and typical payback in less than 5 years. So I have about 10 more slides that I'm going to talk about to kind of conclude, and then we can move to some questions. On the left is the report cover from the work that we did in the Pacific Northwest that concluded in 2010. You can access that on our website today, and that was really the backbone for the work that I just talked about. On the right is the cover of the AEDG, the Advanced Energy Design Guide for Large Hospitals. And it is an ASHRAE document, and we worked really closely with the team that developed this guide. I want to put it up here as a resource for you to be able to look at. It's a great resource and really complements Targeting 100. We had similar energy goals. We collaborated on our energy models to make sure that they were in alignment. They were not at the beginning. If you see early reports of this, you'll see their baselines are up to 450 kb2 per square foot year. We got those aligned. Another thing that is complementary about this is they looked at alternative building mechanical systems. So they're looking at distributed heat pump systems, 4-pipe fan coil units. So it has some more information about other systems that you might put in. It doesn't talk about costing, and they didn't really work with professionals in the field. So we feel like that's what kind of differentiates our work there. On the cover of this is that Swedish Issaquah example that I spoke about. So it is what we like to characterize as on the path to Target 100. Right now it's performing at 114 kb2 per square foot year. It was modeled at 125. So it's working better than they anticipated, which is really exciting. And this is just on the left, energy use breakdown that their engineers did, showing where the heating is going. They used a VAV system, so they're not decoupling, and at the core of the plant is a heat recovery chiller. So you can see that there's more space heating than a Targeting 100 hospital because they did not decouple, but they're meeting a really aggressive EUI. So it's a really great example to look at that's on the path to that Targeting 100 goal. And there's that largest PSE incentive, $4.2 million for that project. These are other projects listing down on the right that we at the Integrated Design Lab at University of Washington in Seattle have worked on. So we've touched these projects in different ways. Swedish Issaquah, we worked with all through the master planning, through the construction, with the 2 different architecture teams that worked on it and the mechanical engineering team. So we had a lot of involvement in that Swedish Issaquah project. But we're really excited about, this is chronological, and looking at these blue EUIs, they're starting to step down, which is really exciting. Starting with Providence Everett at 200 kb2 per square foot year, which is really great. It's lower than an national average hospital. Down to this Peace Island Medical Center at 115, Swedish Issaquah operating, it says 125 here, it's operating at about this. So we're excited about how these EUIs are progressively reducing, and really they're on the path to Targeting 100. Another example of a project that we worked on is a new tower. It's called the Montlake Tower at the University of Washington Medical Center. I'll just talk about it briefly. Essentially, it's a hospital that had no site. This is the existing medical center. It's on the Montlake Cut, if any of you know Seattle well, and it has a beautiful south prominent view to Mount Rainier, which is what that picture is of. And we were involved in this project really from the beginning and working, you can see Joel here, who's the director of our lab, working in visioning sessions, goal setting for the project. Lots of different strategies were put on the table as potentially fundamental for this project. We did extensive with the white group. We do this now with Solaric Architecture and Engineering, but a bundle of strategies doing energy modeling to figure out what was going to be the most cost effective. And ultimately what happened here was massive turn down in the operating room, saved a lot of energy, a heat recovery chiller, and something that was really important to the project team was patient comfort in the patient rooms. These are really severely sick patients that are here, mostly oncology and transplant patients. So here's a rendering of the tower, and the payback on this project was really great. It was, I think, a 1-year payback with the utility incentives. So it was a no-brainer for the hospital to do this. They're gonna capture all those savings year after year. So as I mentioned, this is a little snapshot of our tool that we're developing that will package all this information online. We're in the midst of developing this, due to deliver it by the end of the year, which is really soon. So if you go to our website now, there's a lot of information there, but we'll then connect this to the website, and I'm happy to give you my card, which has our web address on it. What's next for us? We think that, and through our conversations with these peer review groups, that one of the barriers to implementation is knowing that there are examples that have set the precedent before, really trying to reduce that perceived risk of something new. We think the way to do this is to develop a peer-to-peer type exchange. Labs 21 did this about 10 years ago. Is anybody familiar with the Labs 21 program? So some people, essentially it was DOE and EPA got together and developed a program for labs to try to meet really aggressive energy goals. And at that time, there was not a lot of resources for labs, and they developed a program that's now self-sustaining called Labs 21, Labs for the 21st Century. We think there's a need in healthcare for a conversation around energy efficiency in healthcare. There's some organizations that do that some, but not a focused peer-to-peer kind of relationship. And under that umbrella, I mentioned targeting zero. So the path to targeting zero, how do we get there? How do we get beyond 100? Deep renovations, that's a huge next step for us. We think that new construction is great. There's a lot of new construction happening nationally. There's a lot of need for retrofits in healthcare. And rather than replacing old buildings, being able to retrofit and make them relevant again. We think a lot of the targeting 100 strategies actually work really well with deep renovations. And then some other work that I'm doing relates to interior environmental quality and the health of the built environment. So I think I'll leave it at that and open it up for questions. Gunnar.
Did you guys, or is it provided in the tool beyond payback, present value, or maybe enterprise value?
Yeah, we struggle with that. You know, we don't want to talk about simple payback really, because that's really simplifies it beyond what the real value is. But we also know that each organization has their own method for developing their net present value. So I think we'll have a balance of that. I think we will show some of that, because it's fundamentally, when you're making a decision, you want to know that it makes sense financially. So
what if they could plug in their own discount rates and all that kind of stuff?
that would be great. A calculator is,
I would use this discount rate in this period.
One of the things that I didn't put in that next steps is we're developing this tool. We will continue to develop the tool. You know, we have more ideas than we can implement by the end of the year. And to me, a calculator with utility rate and discount rate and really personalizing it to your organization would make a lot of sense. Jake?
You might have mentioned this when you're talking about the different HVAC systems. Was there a predominant plant strategy that you found in the Scandinavian hospitals that were really high performance?
Yeah, that's a really good question. And ultimately, the Plant 4, the ground coupled heat pump plant, was the first high performance model that we developed. And we decided as a group back 6 years ago, let's do a baseline and put the stake in the ground as far as we can and make the most efficient system we can. And we based that high performance scheme 4 on the Scandinavian examples. We said, what did we learn there and what can we apply here? And at the plant level, ground source heat pump plants is what they do. I mean, just if we look at new construction or recently finished, Akershus Hospital has a big ground source heat pump plant. And under construction now, the new Karolinska Hospital has a huge ground source heat pump plant. And it's an urban hospital. And so they're able to get those bore fields into the bedrock underneath the facility and skirt all the infrastructure that they're dealing with as well. So I think that answers your question. The other thing I was going to say is we put that stake in the ground way out there, and then we got feedback from our peer groups that said, what if we don't have the budget, space, or time in construction to develop that bore field? What is an alternative option? And so that's where that heat recovery chiller option came from, and where the distributed heating plant option came from. And the distributed heat option is really, it's a natural gas-fired plant. So we wanted an electric plant, the heat recovery chiller, and a gas-fired plant, which is that distributed heating plant. So we have different options depending on what the ownership team is open for. So.
Which one lends itself best to the retrofit, the distributed heat?
That's a good question. Probably, I think about that more in terms of the building mechanical systems than the plant. Often there's an existing plant that serves one building or multiple buildings and an agglomeration of buildings over time. If we can reduce the load at the building side, we don't have to replace the plant as soon. Or if we're building a new building and we implement more energy efficient solutions, we won't have to add another boiler to the plant. We can just add the building and it'll still be served by that plant. Floor-to-floor heights work well with water-based systems also. So.
Floor-to-floor heights is one of the biggest problems with the old facilities.
Exactly. So, often you're working with 12, 13-foot floor-to-floor. University of Washington, I think, is a 13 floor-to-floor. And so in order to even build a new building, they want to make each floor match. And so fundamentally, that new tower, it's 13 feet floor-to-floor, so each floor matches. And so if you can get a more efficient in size mechanical system, which that decoupled system is, it makes more sense in that kind of application. Jake.
Someone else feel free to jump in. Were there any measures that didn't make the final cut for you to present? Like, did you try doing overinstated envelopes that turned out not to save as much energy as you thought, or was too expensive?
Yeah, definitely. I mean, we had a really creative and ambitious team, that we wanted to do everything, but we just couldn't. One of the big ones is cogen. We just decided as a team to not do cogen. In places like Chicago and New York, they're very interested in cogen, essentially using the heat from the cogen plant and putting it back into the hospital, developing your own energy source on site. And we decided not to do that as a plant strategy. We decided if you decided to do cogen, first you need to reduce your loads. It's not a silver bullet to just serve a higher load regime. Things like facade, there's a million things we could have done on the facade, but ultimately the energy issues are not in the facade of the hospital. It's in solar control. But maybe when you get down to 50, and that's next step for us, the envelope and having a higher performance envelope will make a bigger difference. But when we're going from 250 down to 100, the envelope didn't make a big difference. And we hated hearing that as architects, but it's solar control is the issue there.
Did you find that fixed or the dynamic was dynamic absolutely necessary?
We think, I am partial to dynamic in that they're open when you don't need them. You have more view, you have more daylight coming in. A fixed solution, and especially in a place like Seattle, it might come from my cultural climate. to have a fixed solution on a gray day is just cutting down light when the light's already low. So the dynamic option will pull up out of the way when you don't need it, and it'll only be closed when there are those direct solar days. And it'll move, like if you're on the west facade, it'll only be closed in the afternoon. It'll be moved out of the way during the morning. And so I'm partial to the dynamic. There are issues with it. It's a new kind of technology here in the US. It's all over the place in Europe. So it works. It's new. So, anybody else out here have questions before I call on Jake again? Okay. Jake, I'm glad you guys have questions.
I had a question on the radiant system. So, do you know why they didn't go with like an in-floor or in-ceiling radiant system where the pipes are embedded within a concrete mass, or going with the panels made more sense, cost or performance?
Yeah, that's a good question. I think, I'm trying to think about what our decision making was on that. I think it's partially with flexibility of being able to change. Like often a patient floor is built out and then it'll change 7 years later. It was designed 14 years ago, built, when it first opens at 7 years old, and then, practices change. So I think it makes it more flexible. I think it also has to do with the displacement ventilation, the CFD modeling, but it's a really good question. That was another thing that was on the plate for us, and we decided not to look at it as thermal mass. What does having a thick concrete structure, how does that help us? We didn't go there in this project. We kind of lovingly joked about this project that it's a black hole project, that we could just go down roads like forever and lines of inquiry, but we just had to focus on certain things.
A question for you.
Yeah.
I guess with my work here at IDL, we work with a lot of building operators.
Yeah.
And what type of response did you get with the building operators at the hospitals you visited?
Yeah, I think that's a great question. And that we were really concerned about that too, that the people that are operating these facilities are fundamental for them to be working at how they're intended to work. And in the Pacific, when we first did this work, we had decided to use 4-pipe fan coil units. This is just an example of how we worked with facility operators. For the building mechanical system, instead of the displacement with the radiant sources, we used 4-pipe fan coil units. And that got relative resistance from the people that are taking care of buildings. Some love them and some hate them. And the people that don't care for them as much think that it's more maintenance. It's a lot of ongoing care to take care of them, changing filters throughout the facility, and a sense that it really requires more from the maintenance staff. And so as a team, we decided to take those out and implement a system that seems to take relative less care to maintain. So those radiant sources, they just work. You don't have to change the filter on a monthly or annual basis. And the displacement ventilation system is it's straightforward. So we wanted to provide a system that makes sense. And one of the things that we also left off the table and that there's interest in knowing is, what is the operational impact here? That there are some systems that are harder to maintain, that are more complex than a typical operator might look at, like a boiler and a chiller is pretty straightforward. Heat recovery chiller, if you've never worked with one, it might be complicated. We did not go down the road of trying to develop cost implications for operations, but I think that would be a really interesting next step to look at. And what's the relative difference between even our 4 plant options? We think that there's high buy-in on all the options we chose, ultimately, but that doesn't put a number to it. Anybody else? Well, thanks for having me here today, and I've really enjoyed talking with you, and I really enjoyed your interaction and questions and interest in this project. Thank you.